Welcome, curious minds, to another deep dive. Today, I want you to take a moment right now and just consider the ground beneath your feet. No, not the actual earth, but the floor you're standing on. It's a surface we use constantly, walk on, place our furniture on, live our lives on. But how much do we truly understand about what gives it strength, stability, and even its unique personality?
Probably not much for most people.
Right. The hidden world beneath that visible surface is often overlooked. Here at the Deep Dive, our mission is to take a stack of your sources, articles, research, our own notes, and extract the most important nuggets of knowledge, the surprising facts, and those aha moments that genuinely make you well-informed.
Yeah, digging into the details.
Exactly. Today, we are quite literally diving into the very literal foundations of our built world, floor systems and floor materials. It's a journey from the invisible engineering to the visible finishes. Our material for this particular deep dive comes from a rich set of excerpts focused on architectural principles and construction, specifically detailing the incredible engineering behind floors.
It's pretty technical stuff, but fascinating when you break it down.
Totally. It's a goldmine of technical yet utterly fascinating information that, for most of us, completely goes unseen. So, as we embark on this journey, the big question we're exploring is, what exactly makes a floor a floor?
Fundamentally, what is it doing?
Yes. And how do engineers and builders decide what type of system to use from the myriad of options available? What are the underlying principles that guide these choices? Let's unpack this and explore the hidden complexity of these absolutely essential horizontal planes.
It's remarkable, isn't it, how something so commonplace, something we interact with every moment we're inside a building, is actually so incredibly complex, engineered down to the millimeter.
Right.
Most people just see the finished surface, but beneath that, there's a whole world of structural brilliance, a silent symphony of forces at play.
Okay, so let's unpack this. Our source defines floor systems as simply horizontal planes. That sounds almost deceptively simple, right? It barely hints at the immense responsibility these planes carry. What are they actually doing for us in a building, beyond just being flat surfaces?
Well, the fundamental principle here is that these horizontal planes are the primary load bearers in a structure. They aren't just flat surfaces for walking on. They are meticulously engineered to support immense weight.
Immense weight.
Think about it. A floor has to hold up everything from the building materials themselves, the walls above it, the furniture, and crucially, all the people moving around inside.
Wow.
This includes both static weight, which is constant, and dynamic weight, which changes. It's a constant balancing act.
And our source clearly distinguishes between two critical types of weight: live loads and dead loads.
Ah, yes, that's crucial.
For someone who isn't an engineer, it might just sound like two different kinds of heavy stuff. Is this just a technicality, or is there a real-world consequence if a builder gets this wrong? It seems like it could be huge.
Oh, it's absolutely not a technicality.
Yeah.
You've hit on perhaps the most critical distinction in structural design. If you confuse these two or underestimate them, you could literally have a catastrophic failure. Absolutely. Live loads are the variable elements. Imagine a bustling office floor. You have people walking across a room, furniture being rearranged, movable equipment like filing cabinets or medical devices being shifted. They are transient and unpredictable in their exact location and magnitude.
Okay, things that change.
Exactly. In contrast, dead loads are the constant inherent weight of the structure itself. The concrete, the steel beams, the wood joists, the permanent fixtures, and even the finished flooring materials. These are always there, always applying pressure.
Got it. The fixed stuff.
Right. Understanding this distinction is absolutely critical because it directly dictates the structural requirements and the necessary safety margins that engineers must incorporate into their designs.
Yeah.
You have to account for the worst-case scenario of both types of loads acting simultaneously, ensuring the building remains safe and stable under all conditions. It's the difference between a building standing firm for decades and one that might sadly buckle under unexpected stress.
Okay, that makes total sense. Huge difference. So these floors are holding all this weight, both constant and variable. But that weight can't just hang there, right? Our source says they must transfer their loads horizontally across space. What does that mean in practical terms? Where does that weight ultimately go? It makes you think, doesn't it? The sheer invisible force traveling down.
It really does.
I once saw a video of a controlled demolition. It's mind-boggling how precisely they have to cut those paths for the forces to follow, or else the building just goes sideways.
Absolutely, and that's the real-world consequence of understanding these load paths. If we connect this to the bigger picture, it's about a chain of support, A carefully orchestrated flow.
A flow?
Those loads aren't just magically disappearing or dissipating randomly. They're efficiently distributed and channeled from the floor system to the vertical supports of the building.
Vertical supports, like columns.
Either sturdy beams and columns in a framed structure, or thick, load-bearing walls in a different architectural approach. This transfer ensures that the entire building acts as a cohesive, integrated unit, safely directing all of those forces from the lightest person walking to the heaviest piece of equipment down to the foundation.
Or all the way down.
Which then distributes them safely into the ground. It's a continuous, invisible path for the forces, a fundamental principle of structural integrity.
Okay, here's where it gets really interesting and, frankly, a bit mind-bending. Our source also mentions rigid floor planes being designed to serve as horizontal diaphragms that act as thin, wide beams in transferring lateral forces to shear walls.
Right, the diaphragm action, that's key.
That sounds incredibly complex, but also incredibly crucial for a building's survival, especially in certain parts of the world. What exactly is a lateral force in this context, and why would floors need to act as diaphragms?
Okay, so the concept of a diaphragm is where buildings truly become active participants in their own survival. This is a critical concept for a building's resilience, especially in areas prone to natural disasters like earthquakes or hurricanes.
Like sideways forces?
Exactly. Lateral forces are horizontal forces, meaning they push or pull a building sideways. The most common examples are intense wind pressure, or the ground movement caused by seismic activity, like an earthquake.
Okay.
Without proper resistance to these forces, a building could essentially twist, rack, or even collapse.
Right.
When floors are designed as diaphragms, they essentially act like incredibly stiff, rigid plates that tie all the vertical elements of the building, the columns and walls together.
Like a solid sheet connecting everything.
Precisely. Imagine taking a stack of playing cards. If you push it from the side, it collapses into a mess.
Yeah.
But if you glue rigid plates to the diaphragms between each card, the whole stack moves as one, much more stably. That's what a diaphragm does.
Ah, okay, I get it now.
It ensures the building moves as a single, much stronger entity, orchestrating a complex dance of forces, funneling everything sideways, directly to the shear walls.
Shear walls. Those are the strong ones.
Yes, they're specifically designed to resist and absorb those lateral forces, guiding them safely down to the foundation. This seemingly simple design element is the unsung hero that allows modern architecture to defy nature's most brutal attacks. It allows a building to move as a unified, resilient whole, rather than tearing itself apart under pressure.
Wow. So it's not just about supporting weight from above, but also about protecting the building from sideways pressures, wind, earthquakes, all those horizontal forces.
Exactly. It's a multitasker.
It's truly incredible how much intricate thought goes into something we just take for granted. Now, with that understanding of what floors do, let's peel back another layer and look at the actual materials that make up these marvels, starting with the metallic backbone of so many modern structures, steel floor systems. All right, let's dive into the first major category our source outlines, steel floor systems. When we think of modern, large-scale construction, steel often comes to mind.
Definitely. It's ubiquitous.
What makes steel such a compelling choice for flooring systems? What are its inherent advantages that make it so popular in contemporary architecture?
Well, the true brilliance of steel lies in its incredible strength-to-weight ratio. It can support an enormous amount of weight without being excessively heavy itself.
Strong but light-ish.
Relatively speaking, yes. Beyond that, it boasts remarkable versatility in how it can be fabricated, shaped, and joined, allowing for complex and innovative designs. Our source highlights two key types of steel floor systems, each with its own specific advantages and considerations, allowing builders and engineers to choose precisely based on project needs, budget, and desired performance.
Let's start with the first type, tubular frame flooring.
Right.
This sounds like a really lightweight, almost modular and adaptable option, perhaps something you'd see in residential extensions or less heavy-duty commercial applications. Our source mentions steel joists, angular bars, and GI galvanized iron square tubes. How do these specific pieces fit together to create this kind of floor system, and what's the construction process like from a practical perspective?
It's definitely a layered and precise approach designed for relative speed and efficiency. The process begins with the primary support system, steel joists.
Okay, the joists first.
These are structural elements, essentially lightweight I-beams, that are spaced very precisely, usually at 0.30 meters or roughly 12 inches on center. They form the main parallel framework for the floor.
Got it.
Next, angular bars, which are L-shaped steel sections, are securely attached to the main concrete beams of the building's primary structure. These act as anchors.
Okay, anchors to the main building.
Then the crucial GI, that's galvanized iron squared tubes, are introduced. These are typically common sizes like 2 by 4 or 2 by 3 inches, with an ideal thickness of 1.5 millimeters, and they're fastened directly to those angular bars. This creates a robust, grid-like framework that's surprisingly light.
A light grid.
Once that framework is in place, the subflooring is applied. This usually consists of large sheets of plywood or fiber cement boards, which are then screwed directly onto the steel joists, creating a solid, stable surface for the final floor finishing. It's a system that can be erected quite quickly, saving considerable time on site.
And the source lists some really appealing advantages for this tubular frame flooring. Less expensive, faster installation, lightweight, and workability. Easy to drill for electrical plumbing work.
Yes, those are big pluses.
Why are these benefits so significant, not just for builders and project timelines, but also for the future owners of the building?
Well, these pros speak directly to efficiency, adaptability, and often cost effectiveness, all of which are highly valued in construction. Less expensive and faster installation translate directly into significant savings in both project time and overall budget.
Time is money, right?
Absolutely. In construction, time truly is money, so anything that speeds up the process without compromising safety is a major benefit. Being lightweight is particularly crucial for certain applications, especially when adding extensions, for instance, an additional floor on top of an existing structure.
Ah, like a second-story addition.
Exactly. It minimizes the additional load on the existing foundations and lower structural elements, which might not have been initially designed for a heavier system like concrete. This can avoid costly foundation upgrades.
Makes sense.
And the workability, the ease of drilling for utilities like electrical wiring, plumbing lines, or even HVAC ducts, makes both the initial fit-out and any future renovations much simpler and less costly. Imagine trying to cut through a solid concrete slab for a new drain line versus drilling through this.
Much easier.
Much. The source specifically points out it's perfect for upper floor extension, which is a clear, practical application where these benefits truly shine, offering flexibility for growth without massive structural overhauls.
Okay, so it's clearly a smart choice for certain scenarios, but every system has its trade-offs, right?
Always.
Our source points out some clear limitations for tubular frame flooring. It's less durable, prone to corrosion, offers poor soundproofing, and has limited floor finishings. Can you elaborate on these drawbacks and what they mean for the long-term performance and livability of a building using this system? Because less durable sounds like a big red flag.
It definitely highlights the balance you have to strike between initial cost and long-term performance. When the source says less durable, it implies that the system might have a shorter lifespan compared to more robust options like solid concrete, or it might be less resistant to heavy impact or continuous high-traffic wear and tear over many decades.
So maybe not for factory floor.
Probably not, no. It's built for lighter loads and less abuse. Prone to corrosion is a significant concern because steel, even galvanized iron, can rust, especially in humid environments, or if protective coatings are compromised through scratches or inadequate treatment.
Like near the coast.
Potentially, or just very humid areas. This necessitates proper surface treatment, regular maintenance, and careful consideration of the environment where it's used. You wouldn't want this in a perpetually damp basement, for instance.
Right.
Coarse soundproofing is a major issue for livability. It means that noise, whether it's footsteps from upstairs, voices, music, or even the subtle creaks of a structure settling, can easily transmit between floors.
Ugh, noisy neighbors.
Exactly. This is a critical consideration for multi-story residential buildings, apartments, or even quiet office spaces where acoustic privacy and comfort are important. And finally, the limitation to lightweight floor finishings like vinyl tiles, linoleum, or thin laminates means you simply cannot install heavier, more luxurious materials like thick natural stone tiles, ceramics, or dense hardwoods that require very rigid and unyielding subfloor.
So no marble floors on this system.
Definitely not. This impacts both the aesthetic choices and the functional capabilities of the space, preventing certain high-end finishes.
Okay, that gives us a much clearer picture of where tubular frame shines and where it struggles. Let's move to the second type of steel system our source highlights. Steel deck flooring.
Ah, steel deck. A different beast altogether.
It mentions the use of high-performance galvanized steel sheets. This sounds like a significantly different approach from the tubular frame, perhaps something more substantial. What are the big wins here, the major advantages of using steel deck flooring?
Okay, the true brilliance of steel deck flooring lies in its shift to a composite structure, which fundamentally changes its performance and offers profound benefits.
Composite, meaning steel and concrete together.
Exactly. With steel deck flooring, the high-performance galvanized steel sheets themselves become an integral, permanent part of the floor slab once concrete is poured over them. This collaboration between the steel and concrete creates a highly efficient and incredibly strong composite material, leveraging the best properties of both. The steel acts as both formwork and tensile reinforcement.
Okay, so it does double duty.
Precisely. This leads to several strong advantages.
Hmm.
It's lighter than a full, solid concrete slab of equivalent strength because the steel deck acts as permanent formwork and also contributes structurally, allowing for decreased slab thickness while maintaining load capacity.
Lighter but strong.
Yet it's simultaneously more durable, precisely because it forms this composite structure of the building, meaning it benefits from the incredible compressive strength of concrete and the tensile strength of steel working together.
Best of both worlds.
Installation is faster with less formworks involved because the steel deck itself eliminates much of the temporary shoring and molds that would otherwise be needed for a traditional concrete pour. It's also often ceiling ready immediately after installation,
Oh, interesting.
as the underside of the deck can often be painted directly or left exposed, saving finishing time and cost. Plus, it offers excellent termite and fire-resistant properties, which are absolutely crucial for safety, longevity, and often building code compliance.
Those are some truly impressive pros addressing key concerns for durability, cost, and safety. It almost sounds like a magic bullet for so many construction challenges. Lighter, faster, durable, fire-resistant. It almost sounds too good to be true.
Chuckles, well.
What's the catch? Are there situations where the system simply won't work or where its supposed advantages start to crumble? Our source mentions availability and being prone to corrosion, not ideal for beach houses.
You're right to be skeptical, because even highly advanced systems have their limitations, and understanding them is key to smart design. Availability can certainly be a logistical challenge depending on the specific location of the construction project.
Right, can you even get the stuff?
Exactly. If the specialized steel deck material isn't readily available in the local market, it can dramatically impact project timelines, significantly increase shipping costs, and complicate procurement, potentially negating some of those faster installation benefits.
Okay, logistics.
And the corrosion issue is a key takeaway and a vital environmental consideration. While galvanized steel is designed to resist rust, it still has limitations, especially in highly corrosive environments. Coastal areas, specifically mentioned as not ideal for beach houses in the source, are classic examples where high salt content in the air and pervasive humidity can significantly accelerate corrosion, even on galvanized surfaces.
So that salt air really eats away at it.
It can, yeah. Imagine the salt spray constantly hitting the underside of that deck. This highlights that even robust materials have specific environmental vulnerabilities that must be thoroughly considered during the design and planning phases to ensure long-term structural integrity and prevent costly premature failures. It's about matching the material to its intended environment.
From the modern marvels of steel, let's turn to a more traditional, yet still incredibly vital and widely used system. Wood floors.
Ah, the classics.
It's a classic for a reason. Our source provides a fantastic glossary of terms here, which are essentially the building blocks of any sturdy wood floor. It's like learning the anatomy of a floor. Let's unpack these essential components because they really are fundamental to understanding how these floors come together.
The beauty of wood systems lies in their apparent simplicity, yet each component plays a precise and critical role. Understanding these terms is truly like learning the grammar of a building. It reveals the intelligence behind a material that has been used for centuries.
Let's start from the very bottom, where the wood structure meets the foundation. Our source mentions the sill plate.
The sill plate.
What exactly is a sill plate, and what foundational role does it play in a wood structure? It sounds pretty important if it's right there at the start.
The sill plate is truly foundational in wood frame construction. It's the horizontal timber, typically a piece of pressure-treated lumber for moisture and pest resistance, that sits at the very bottom of the entire wood structure's frame.
Right on the concrete.
It rests directly on the building's concrete or masonry foundation. Its essential role is to provide a continuous, even-bearing surface that distributes the weight of the entire wall and floor system uniformly to the foundation below.
Okay, spreads the load.
Exactly. Imagine trying to put wooden posts directly onto uneven concrete. It wouldn't work.
Yeah.
The sill plate acts as that critical uniform connection point between the wood frame, which is dynamic and susceptible to rot, and the inert, more durable foundation. It's often anchored to the foundation with bolts to resist uplift forces from wind.
Then we have the girder. Our source calls it a large or principal beam.
Yep, the girder.
Why is it so important, and how does it fit into the overall support structure? Is it like the main highway for all the weight coming down?
That's a good way to think of it. Girders are absolutely the heavy lifters of a wood floor system. They are indeed a large or principal beam specifically designed to support concentrated loads.
Concentrated loads, like from walls.
These loads often come from isolated points along its length, such as the ends of multiple floor joists, or even from columns or bearing walls that are aligned directly above the girder. Think of them as the main arteries supporting the entire floor system, taking the cumulative weight from a large section of the floor and channeling it down to the posts or columns that support the girder itself.
So they're bigger than the joists.
Oh yeah, substantially larger and stronger than individual joists, because they are carrying the weight from a much larger area. Without a properly sized girder, a floor could sag dramatically or even fail in the middle of a large span.
This one has a few names, according to our source: joist header, rim joist, or band joist.
Right, the rim joist or band joist, same thing.
What's its specific job in a wood floor system, and where would we typically find it? It sounds like it's holding things together at the edges.
It is, exactly.
Yeah.
This component is absolutely critical for lateral stability and for essentially closing off the floor platform. The joist header, rim joist or band joist, runs perpendicular to the main floor joists.
Around the outside.
Yes, you'd find it forming the outer edge of the entire floor platform, essentially framing the perimeter of the floor like a belt around the waist of the structure. Its specific job is to provide crucial lateral support to the ends of the floor joists, preventing them from twisting, buckling, or rotating out of plane under load.
Keeps the joist straight at the ends.
It also closes off the ends of the joist bays, providing a neat finish and a solid surface for exterior sheathing or finishes to attach to. It really ties the whole system together at the perimeter, distributing forces evenly to the supporting walls or girders.
So we've got the foundational pieces, the main girders, and the perimeter defined. Now, how do we actually create the surface we walk on? I'm guessing that's where the floor joists come in.
Bingo.
These seem like the unsung heroes, just repeating across the span. What's their specific job, and how do they really tie into the whole system to create a solid, non-bouncy floor?
Exactly. The floor joists are the tireless workhorses, the backbone of the floor itself. These are one of a series of parallel beams of timber that directly support the floor loads across the span of a room.
Okay, the main supports for the floor itself.
They are supported in turn by the larger elements we just discussed, such as the girders, or by load-bearing walls. Their function is to carry the weight of the subfloor, the finished flooring, and all the live and dead loads above them, transferring that weight efficiently to their supports.
Gotcha.
They are the most numerous structural elements in a typical wood floor, and their size and spacing determine the stiffness and load-bearing capacity of the floor. If you have a bouncy floor, it's often because the joists are undersized or too far apart for the span.
Ugh, the dreaded bouncy floor. Below the finished surface, but directly above the joists, we have the subfloor.
Yep, the subfloor, critical layer.
What is its specific purpose, and why is it so important even though it's completely hidden once the house is built? It seems like it's just a temporary layer.
Oh, the subfloor is anything but temporary. It's absolutely crucial. It's the initial layer of solid material, typically large sheets of plywood or OSB, oriented strand board.
OSB, right.
That is placed directly above and securely fastened to the joists. Its purpose is multifaceted. It creates a stable, continuous, and smooth surface upon which the finished flooring can be installed without dips or unevenness.
So the finished floor lays flat.
Precisely. It also plays a crucial role in distributing concentrated loads, like the weight of a heavy piece of furniture or the impact from a dropped item across a much wider area of the joists. Without a proper subfloor, walking directly on joists would be impossible, and finished flooring would buckle, crack, or even punch through between the joists.
Right, you'd fall through.
Well, hopefully not. But the floor wouldn't work. It ties the whole top surface together, ensuring rigidity and performance.
Finally, we have blocking or bridging. Our source says these are short boards which are fixed vertically between floor joists to stiffen them.
Blocking or bridging. important detail.
Why is this extra step necessary? Don't the joists alone provide enough stiffness, especially if they're properly sized? It sounds like an added complexity.
It does seem like extra work, but this raises an important question about overall structural integrity and performance that goes beyond just vertical strength. While individual floor joists are designed to be strong under vertical loads, especially over longer spans, they can be susceptible to twisting, rotating, or buckling sideways under pressure.
Like they could flop over.
Kind of, yeah, much like a thin ruler trying to stand on its edge. Blocking or bridging prevents this by providing crucial lateral support to the joists. These short pieces of wood are installed perpendicularly between the joists, either in a straight line, blocking, or in a crisscross pattern, bridging, typically at midspan or at specified intervals.
Okay, it connects the joists together sideways.
Exactly. By tying the joists together at these intervals, they essentially brace each other, making the entire floor system much more rigid and stable. This significantly reduces unwanted bounce, deflection, or vibration in the floor, which can be incredibly annoying for occupants.
Ah, so that's why some floors feel more solid.
It's often a big part of it, yes. It dramatically improves the feeling of solidity and the overall long-term performance and comfort of the floor.
Now, let's shift gears completely and delve into concrete floor systems, often known as suspended concrete slabs.
Right, moving into the heavy stuff.
When we typically think of concrete, our minds might first go to foundations or ground-level slabs, but it's clearly a major player in elevated floors too, especially in larger multi-story buildings. What truly sets concrete floor systems apart from wood or steel joist systems? What's the fundamental difference in how they're supported?
Concrete offers immense compressive strength, exceptional durability, and excellent fire resistance, making it a staple in multi-story and high-load construction. What differentiates it structurally from the systems we just discussed is that here, beams are the primary structural support instead of joists.
Beams, not joists, got it.
While concrete slabs can be quite thick and heavy, they are poured as a monolithic unit, meaning they cure into a single, incredibly rigid, unyielding structure.
This gives them a fundamentally different character and capacity compared to the assembled nature of wood or steel joist floors.
What are some of the fundamental steps and key materials involved in creating one of these massive suspended concrete slabs? Our source mentions formworks, reinforced steel bars, and even a very specific 28 days curing time. This sounds like a much more involved and precise process than simply screwing down some plywood, with a lot less room for error. It definitely is a more complex, time-intensive, and highly engineered process where precision is paramount. It first entails precise formworks, which are temporary molds that are meticulously built to hold the wet concrete until it gains sufficient strength and cures.
The molds for the concrete.
Right. Our source indicates these are often made of phenolic boards, chosen for their smooth surface and durability, which allow for a good, uniform finish on the underside of the slab. Absolutely essential for structural strength are reinforced steel bars, commonly known as rebar.
Rebar, yeah.
These steel bars are carefully calculated, cut, and placed within the formwork before the concrete is poured. This is critical because while concrete is incredibly strong in compression, meaning it can resist crushing forces very well, it is relatively weak in tension, or resisting pulling or stretching forces.
So the steel handles the pulling.
Exactly. The rebar provides that crucial tensile strength, allowing the concrete element to effectively resist bending and stretching under load. Finally, the 28 days curing time is absolutely crucial.
Why so long?
This is the scientifically determined period during which the concrete chemically hardens and gains its designed structural strength effectively. Rushing this process, or not maintaining proper moisture and temperature during curing, can significantly compromise the integrity and long-term performance of the entire structure.
Okay, patience is key.
It's not just a suggestion, it's a structural requirement that ensures safety and longevity.
Our source specifically highlights concrete rebar spacers. These seem like such small, unassuming components, little plastic or concrete bits. But what critical role do they play in such a massive, robust structure like a concrete slab? They seem almost insignificant in the face of tons of concrete and steel.
It's funny you say that because what's fascinating here is the attention to detail that ensures structural integrity at every level, right down to these tiny components.
Really?
Yeah. Rebar spacers, often small plastic or concrete chairs or blocks, are critical for maintaining the correct spacing between the rebars themselves, and even more importantly, ensuring they are properly positioned within the concrete mass.
So they hold the rebar in the right spot.
Precisely. This precise placement guarantees structural stability and, crucially, ensures the required concrete thickness, or cover, around the rebar. This concrete cover is vital for several reasons. It allows the steel to perform its reinforcing function properly by bonding fully with the concrete, preventing any slippage. Even more importantly, it provides essential protection to the steel, preventing it from corroding due to exposure to moisture, air, or chemicals. Rusting rebar expands and can crack the concrete from the inside out, leading to premature structural failure.
Wow, so they protect the steel.
Exactly. So these seemingly insignificant spacers are in fact mighty guardians of the rebar, ensuring the slab's long-term strength and durability.
That makes perfect sense. The details truly matter. Our source then takes us through several distinct types of concrete slabs.
You have lots of variations.
It seems like concrete isn't just one monolithic thing, but a versatile material that can be adapted for a wide variety of structural needs and spans. Let's explore these variations and understand why engineers and architects might choose one type over another. Why so many options?
It's an excellent question why so many types of concrete slabs when it all just seems like concrete. Each variation is meticulously engineered to optimize for specific spans, support different types of loads, and fulfill diverse functional requirements, often balancing efficiency with structural integrity.
Different tools for different jobs.
Pretty much. They offer a range of efficiencies and levels of structural performance, allowing for highly tailored solutions in diverse building applications, from smaller residential homes to massive industrial complexes or towering skyscrapers. It's about optimizing material use and construction methods for a given challenge.
Starting with the one-way slab. What defines this type of concrete slab, and when would it typically be chosen? What's its ideal scenario?
Okay, a one-way slab is characterized by being reinforced in one direction and cast integrally with parallel supporting beams.
Reinforced one way, okay.
This means that the primary structural action and the transfer of loads occur predominantly in a single direction, spanning between those two parallel supports. Imagine a long, narrow corridor in an office building, or a smaller office space within a larger structure.
Where the load clearly goes one way.
Exactly. Here, the load path is incredibly clear, directly from one side to the other. You don't need the complexity or added material of two-way reinforcement. It would actually be inefficient overkill, adding cost and weight for no structural benefit. So choosing a one-way slab here is a fundamental decision for elegance, cost-effectiveness, and simplicity in design and construction.
Makes sense. Keep it simple.
It's about doing precisely what's needed, reliably, without adding unnecessary complexity or material.
Next, we have the one-way joist slab, which our source also calls a ribbed slab.
The ribbed slab.
How does this differ from the basic one-way slab, and what advantage does it offer, especially if you're looking to span longer distances or support heavier loads?
This is an evolution designed for greater efficiency and span capability. A one-way joist slab is cast integrally with a series of closely spaced joists, which are essentially ribs of concrete running in one direction, similar to the joists in a wood system.
So it looks like concrete joists underneath.
Kinda, yeah. You can imagine the underside having a series of parallel concrete beams. The key benefit here is that it's more suitable for longer spans and heavier loads than one-way slabs. The ribs provide significantly increased stiffness and depth to the slab without adding excessive weight.
Saves weight.
Because the concrete between the ribs is thinner or sometimes even absent, forming voids. It's like taking the structural efficiency of an I-beam and repeating it across a wide area.
Okay, efficient shape.
This makes it a much more efficient and economical solution for larger floor areas, such as classrooms in a school, a retail space, or a typical office floor where a simple flat slab would be too thick, too heavy, or require too many intermediate supports. It provides a lighter solution for substantial spans.
Now we move into two-way slab and beam systems. The two-way part sounds significant.
It is significant, yeah.
What's the significance of two-way reinforcement, and how does that change its load-bearing capabilities and where it might be used?
The significance of two-way reinforcement is substantial. It fundamentally changes how the slab behaves under load. This system is reinforced in two directions, both horizontally and perpendicularly, and it's cast integrally with supporting beams on all four sides of each slab panel.
Beams on all four sides, okay.
This arrangement allows the loads to be distributed much more effectively across both axes, leading to a more uniform transfer of forces to all surrounding beams. This makes it Effective for medium spans and heavy loads, a very common choice in many commercial and institutional buildings, like hospitals or university buildings, where larger, more uniformly loaded areas are needed.
Like a big square room.
Exactly. Think of a large lecture hall or an open-plan office. It offers balanced structural performance and good control over deflection, because the load isn't just traveling in one direction, it's being shared across a grid of supports.
The two-way waffle slab sounds particularly intriguing given its name.
Chuckles. Yeah, the waffle slab looks just like it sounds.
What's the distinguishing feature here that gives it that unique name, and what kind of performance does it offer? When would an engineer opt for a waffle over other slab types?
This system has a very distinct appearance, literally resembling a waffle pattern on its underside. It is a two-way concrete slab reinforced by ribs in two directions, creating that characteristic grid.
Okay, ribs both ways.
Now, why the waffle? Imagine trying to span a huge distance with a solid block of concrete. It would be incredibly heavy, thick, and expensive. The genius of the waffle is that by strategically removing concrete from the non-structural areas between the ribs, you significantly reduce the overall weight of the slab while maintaining incredible stiffness and strength.
Takes out weight but keeps the strength in the ribs.
Exactly. It's like taking the best parts of an I-beam and applying them in two dimensions, creating an extremely efficient structural system. This unique geometry allows it to carry heavier loads and span longer distances than flat slabs.
So for really big open spaces.
That's where it shines. For those massive open spaces, like a shopping mall, a multi-story car park, an airport terminal, or a large convention center, where you want to minimize columns and maximize open area below, the waffle slab is your go-to solution. It provides an impressive blend of strength, span, and material efficiency.
And then we have the two-way flat plate. This sounds like the simplest, perhaps most minimalist form of concrete slab construction.
It's pretty straightforward, yeah.
What are its defining characteristics and common uses, and what benefits does its simplicity offer, especially from an architectural or user perspective?
The two-way flat plate is indeed a very clean, simple, and elegant system. It's characterized as a concrete slab of uniform thickness reinforced in two or more directions and supported directly by columns without beams.
No beams at all, just slab and columns.
That's right. That without beams part is key. The major advantage here, and a very practical one for modern construction, is lower floor-to-floor heights. Because there are no projecting beams hanging down, the slab directly connects to the columns, minimizing the vertical space taken up by the structure.
Ah, so you get more headroom, potentially.
Exactly. This makes it particularly practical for apartment and hotel construction, where maximizing ceiling height within a given building envelope and minimizing overall building height to meet zoning regulations or reduce material costs are often priorities. It also streamlines construction by eliminating the complex formwork typically required for beams.
Easier to build.
Generally, yes, and simpler mechanical installations, as ducts and pipes don't have to navigate around beams. It gives a very clean, uninterrupted ceiling line.
Finally, the two-way flat slab. How does this differ from the flat plate we just discussed? It sounds similar, but with a key modification that must offer an advantage.
It is indeed quite similar to the flat plate, but with a crucial enhancement designed to boost its capacity. The two-way flat slab is essentially a flat plate that is thickened at its column supports to increase its shear strength.
Thickened right at the columns.
This thickening, often referred to as a drop panel, a localized increase in slab depth, or a column capital, a flared top on the column itself, is a localized increase in the slab's depth right where it connects to the columns.
Okay, why do that?
This modification directly addresses the very high shear stresses that occur at that critical column-slab connection. By increasing the shear strength at these points, the system can handle even heavier loads or span longer distances than a basic flat plate.
So it beefs it up where it needs it most.
Precisely. While still maintaining many of the flat plate's advantages, like a relatively shallow overall depth and simpler formwork compared to beam systems. It's a smart way to get more load capacity and span potential out of a flat slab without reverting to a full beam and slab system, making it suitable for slightly heavier duty applications than a pure flat plate, while still offering those clean ceiling lines.
We've spent a lot of time dissecting the incredible engineering beneath our feet, understanding the invisible workhorses and colossal structures that support our built world.
A lot going on down there.
Totally. Our source then touches briefly on different floor materials, but interestingly, it immediately presents an activity 3 for research, rather than a direct list of materials. It's almost a pivot point, asking the listener to do the homework.
Yeah, that's an interesting approach. It raises an important question. Why might an educational resource present it this way? While our deep dive has focused intensely on the structural systems, the bones of the floor, the choice of the finished material that's the surface you actually see and walk on, like tiles, wood planks, or carpet, is equally crucial.
The part we actually see and touch.
Exactly. It dictates not just the aesthetics, but also the function, durability, maintenance, and even the user experience of the space. The source, by framing it as an activity, highlights the immense variety and localized nature of these choices. But here at the deep dive, we've already taken that step for you.
Oh,
We
God.
dug into common options, and what immediately stands out is the incredible range and how each choice is a direct conversation with the structural system underneath.
That's a great point. The activity in our source prompts us, the learners, to research on the different floor materials available in the Philippine market. And it asks for a very specific table with specifications like material and finish, size, price per piece, supplier and a bagger brand, and way or method of installation.
Very practical details.
It really drives home the practical application. So let's talk about some of those findings, what we discovered when we did our own little deep dive into this.
Absolutely. This activity isn't just a homework assignment. It's actually a practical blueprint for how to gather real-world, localized knowledge in the field. It emphasizes that the best material choice depends not just on its inherent properties like hardness or water resistance, but also on crucial real-world factors such as local availability, the precise cost per unit, reliable suppliers, and the specific installation requirements and skills needed. Let's take ceramic tiles, for instance, which are hugely popular in many markets, including the Philippines. They're durable, moisture-resistant, and fantastic for wet areas like bathrooms and kitchens.
Classic choice.
But a key insight from our research activity is that while beautiful, they are inherently heavy and require a perfectly rigid, stable subfloor to prevent cracking.
Ah, so back to the structure again.
Exactly. You wouldn't want to put them on a tubular frame system designed for lightweight finishes, right?
Mm-hmm.
The very flex of that system would lead to cracked grout in tiles.
Makes sense.
We found various sizes, from small 4x4-inch squares up to large format 2x4-foot rectangles, with prices varying wildly based on origin and quality, from local producers to imported brands. Installation typically involves a cement-based mortar and grout, requiring skilled labor and careful leveling of the subfloor.
Okay, so tiles need a solid base. What about something like vinyl planks or luxury vinyl tiles, often called LVT? They seem to be gaining a lot of popularity.
They absolutely are, and they highlight the evolution of materials. LVT and vinyl planks offer incredible versatility. From our research, we see them mimicking everything from natural wood to stone, but with far greater water resistance and a softer underfoot feel.
Looks like wood, but isn't.
Pretty much, yeah.
Yeah.
They are relatively lightweight, making them suitable for a wider range of structural systems, including our tubular frame steel floors.
Ah, so these could go on that lighter frame.
Potentially, yes. They come in various thicknesses and wear layers, with common sizes replicating wood planks or square tiles. Installation can be glue down or click lock, often making them a DIY-friendly option, saving on labor costs.
Blick lock. Easier install.
Often, yes. The insight here is their adaptability. They offer aesthetic variety without imposing heavy load demands, and they are forgiving of minor subfloor imperfections, unlike brittle ceramic. Plus, they are incredibly cost-effective, with a wide range of suppliers.
And how about a more traditional option, like wood flooring? Not the structural wood, but the finished surface. Engineered wood, for example, is quite common.
Engineered wood is a fascinating example because it takes the beauty of natural wood and adds structural stability. Unlike solid hardwood, which can expand and contract significantly with changes in humidity, a major factor in tropical climates.
Right, wood moves.
Engineered wood is constructed with multiple layers, typically a plywood or HDF core with a real wood veneer on top. This cross-ply construction makes it much more dimensionally stable.
More stable than solid wood.
Generally, yes, especially regarding humidity changes. Our research shows it comes in various plank widths and lengths, with prices ranging based on the thickness of the veneer and the species of wood. It can be installed floating, stapled, or glued down. The key takeaway here is that it offers the aesthetic of solid wood with much greater resilience to environmental fluctuations, reducing the risk of warping or gapping.
Good for humid places, then.
It can be a better choice than solid wood, definitely. However, like any wood product, it still benefits from a rigid subfloor and isn't ideal for consistently wet areas.
So it's clear that the choice of finished material isn't just aesthetic. It's a performance decision linked directly to everything we've just discussed about loads, rigidity, and environment.
Absolutely, they have to work together.
The structural system is the foundation upon which all these material choices are made, preventing costly mistakes or future failures. Hashtag outro. So what does this all mean for us, the curious learners who spend our lives on these horizontal planes? This deep dive into floor systems and floor materials reveals an astonishing world of engineering and design right beneath our feet.
It really is amazing when you stop to think about it.
From lightweight steel frames perfect for flexible extensions to the incredibly robust and versatile concrete slabs and the timeless appeal of meticulously crafted wood systems, each is a meticulously engineered solution to very specific challenges in construction.
We've seen how architects and engineers must constantly balance a complex array of factors: extreme load capacity, the required span length between supports, long-term durability, the initial cost of materials and labor, installation time, and even the final aesthetics and functional needs of the space.
So many variables.
Indeed. This knowledge isn't just for professional builders or architects. It truly helps you appreciate the profound intelligence embedded in the structures all around you. It even empowers you to make more informed choices for your own living or working spaces, understanding why certain materials are used where they are and what unseen forces they are designed to withstand.
As we wrap up this deep dive, consider this. The next time you walk into a room, don't just feel the solid floor beneath you. Ask yourself, what invisible network of beams, joists, and concrete is silently carrying the immense weight of everything above it? And how does that hidden complexity, that unseen engineering, subtly but profoundly shape the very way you experience the safety, the stability, and even the acoustics of that space?
It's a great question to ponder. How does knowing the structural story of a building change your appreciation for its design, its resilience against the forces of nature, and perhaps even its hidden long-term costs and maintenance needs? The floor is never just a floor. It's a testament to incredible human ingenuity and a silent hero in our daily lives, holding up our entire world, one horizontal plane at a time.